All right, so how are we going to fix this molecule? Silicon's got enough electrons, oxygen has too few. How do we deal with the situation?
You just draw 2 bonds for each.
I could just draw bonds, but those electrons got to come from somewhere. Where are they going to come from?
Like the top and bottom of the silicon.
Right. So the silicon basically can share those extra electrons, not extra electrons, those electrons with oxygen and still get to claim them. So what will happen is basically this pair of electrons goes here to form a second bond, and this pair of electrons goes here to form a second bond. And then we're left with and you'll see sort of a pattern sort of emerging over time. You'll notice that basically carbon, silicon, everybody in group 4, like I mentioned before, makes 4 bonds and has 0 lone pairs. That's typical. Oxygen has 2 lone pairs and 2 bonds. Nitrogen has 1 lone pair and 3 bonds. And you'll see this pattern over and over and over. They're not always single bonds. Sometimes they're double bonds. But that's not the only way you could do this. So this is the most obvious way to write it, because then now each one has 8 total electrons. But we also need to remember each molecule basically for stability wants to have a small amount of formal charge as possible. What is formal charge? You see formal charge here. Anyone give me a definition for formal charge? What does that mean? What does it mean and how do we calculate it? What does it mean for an atom to have a formal charge in a molecule? Certainly has something to do with electrons. Got to start calling on people. Don't want to do that. That's part of it, Ezekiel. That's part of it. We use that rule to calculate formal charge. But what does formal charge actually mean? We use that to calculate it. We assume that all the electrons and bonds are shared equally. That is true. We use that rule. But what does it mean to actually have a formal charge? Like for instance, in this molecule, this oxygen has a formal charge of -1. This oxygen has a formal charge of +1. How do we figure that out? What does that mean?
It means how much were lost or gained.
Lost. How many of what are lost or gained?
Electrons.
So basically, how many electrons, it comes down to how many electrons do we expect an atom to have, and how many does it actually have, okay? So how many do we expect, how many valence electrons do we expect oxygen to have?
Six.
We expect it to have 6, right? Because it's in group 6, so we expect it to have 6. Well, let's look at this structure here and count how many it actually has. So it's got 2, 4, 6, and it gets to count, and this is where, Ezekiel, this is where your rule comes in. It gets to keep one of the electrons from the bond, because we assume that the electrons are shared equally. They're not, but we assume that they're shared equally. So each one of these bonds is 2 electrons, so oxygen gets to keep one of them. So oxygen gets to keep that one, and silicon gets the other one. So it has a total of 7. So we expect it to have 6. It should have 6 valence electrons. It actually has 7, so we subtract 7, and we get a charge of -1. Now the opposite happens to the other oxygen. This oxygen here, we see it has 2 electrons as a lone pair, and 1, 2, 3 in bonds. So that one has a total of 5. We expect it to have 6. So 6 minus 5 equals +1. So that would have a charge of +1. So in molecules, generally, you want to reduce the total amount of formal charge as much as possible. So even though we could draw silicon dioxide that way, this is the preferred structure, because in this structure, nobody has a charge. Here, oxygen has 6 valence electrons, 2 lone pairs, 2 bonds, for a total of 6. The silicon in the middle has 4 valence electrons, 1 in each of 4 bonds. So it doesn't have a charge. So there's no charge at all. So we try and get our Lewis structures to have this few number of formal charges as possible. And you particularly don't want like opposite charges right next to each other. You don't want a positive charge right next to a negative charge. Okay. So for that, like I just said, just have like 9 copies of this. Your chemical formulas, your dot diagrams, total electrons, and the Lewis structure. So for the second one's kind of fun. I'm just going to briefly sort of show you what's going on. Who can tell me what an electron domain is? What's an electron domain? Because we're talking about 2 electron domains, 3 electron domains. What are them? What's an electron domain? For us to look at, okay, I'll just draw water again, because this is my favorite molecule. Whoops, let me go back. So here's water. And when we talk about electron domains, we talk about around the central atom. That's what we're talking about. So how many electron domains are around oxygen? What's an electron domain? Rachel, you got an idea?
Is it something with like the pairs? Like the
It's
yeah.
yes. Yes, it can be a pair of electrons. Not always, but it can be a pair of electrons. Alexander, you have something to add? You can. What else could it be other than a pair of electrons?
I'm not sure.
Okay. Sadie?
I'm not sure.
Okay. Emily? Electron domain. Ooh, Ezekiel's sort of onto something. So Ezekiel says something about the location of the bond, and location is sort of getting us closer to what we're talking about. So anybody have a sort of a loose definition of what an electron domain is? It can be a lone pair, and it can be a bond, but more loosely, it's something else. And you use the word you can use the word location in the title, in the definition. It's basically, that's what the electron domain is. It's a location. It's a location of what? What are we going to find in an electron domain? What's going to be there? It's sort of in the title. What are we going to find in an electron domain? It's kind of a trick question. Electrons, there you go, Sadie, exactly. All it is, and it's a long way of getting to it, electron domain is just a place where you're going to find electrons. That's it. It's just a location of electrons. It's a region of electron density. That's really what we're looking at. It's a region of electron density. So how many regions of electron density are around the central oxygen and water?
4.
4, exactly. We got 1. There's 1 region. There's another region. There's a third region, because remember, each bond is a pair of electrons. So there's 1, 2, 3, 4. So there's 4 regions of electron density. And we can see from this that that means it has 4 electron domains. It has tetrahedral geometry. And what that means is you're going to be able to figure this out for yourself. It's actually, this works much better than I figure it would. So let's do another molecule, and I'll give you an idea of what I'm talking about. So here's another molecule. This is hydrogen cyanide. Ooh, nasty. You don't want to drink this. So here's hydrogen cyanide. How many electron domains are around the central carbon?
4.
Nope. Now remember, a domain is a region. It's an area where there's electrons. They didn't say how many electrons are going to be in that region. It's just a region where you're going to find electrons. So how many regions around that carbon will we find electrons?
2.
2, right, exactly. I'm going to find electrons in this region between the carbon and the hydrogen, and I'm going to find a lot more electrons in the second region between the carbon and the nitrogen. So it's only got 2 regions. One of them has a lot more electrons. This one has, the one on the right has 6 electrons, and the one on the left only has 2. But they're both regions of electron density on opposite sides of the carbon. And since they're on opposite sides of the carbon, what shape do you think that that's going to take? They're on opposite sides. You have 2 electron domains on opposite sides of the carbon. What shape is that going to make the molecule? And we'll figure that out by blowing up these balloons and seeing what shape they take. So just holding them, they automatically take a shape. What shape do they automatically take? What shape is that? So what shape would we say that is? This straight line shape. Linear, exactly. And so it's because, remember, what charge are electrons?
Negative.
They're negative. And so do negative charges, like, are they repelled by each other or attracted to each other? If I have 2 negative charges, are they going to attract or repel?
Repel.
They're going to repel, right? So if I have electrons over here, and I have electrons over here, they are going to want to take a shape to get as far away from each other as they can, because they repel each other. And when there's 2 areas where you have electrons, they're going to naturally form this shape. Now let's look at so linear geometry, 2 electron domains. Let's look at another molecule. Let's look at this one. That is formaldehyde. That's another sort of nasty molecule. You don't want to drink this either. So how many electron domains are around the central carbon?
Three.
3, exactly. There's this one, there's this one, and there's this one. So the third one has twice as many electrons as the first 2, and that will have some influence on the angles that it takes. But the overall shape will be something that has 3 electron domains. So just from the balloons, we take 1, we take 2, we take 3 of them, and we tie them together. And what shape does it take? What shape would you say that is?
A triangle.
The triangle. And is it 3-dimensional or 2-dimensional? I mean, I know it sort of looks 3-dimensional from here, but
2-dimensional.
it's 2-dimensional. It's a plane. You can see that these are all in the same plane. If you look down this axis, you can see they're all in the same plane. So we call that trigonal for triangle, planar. So this gives you, and it shows you what these angles are going to be. The bond angles are going to be about 120 degrees because we have, this is in a plane, so each one of these is going to be 120 degrees separated from each other. And then when we have 4, I did blow up a 4th one. If you have 4, you tie those together, it takes on this shape, where you have 1, 2, 3, 4. You have like a pyramid shape, or what we call a tetrahedron. And because that's the shape where 4 electron domains can get as far away from each other as they possibly can. So what basically all this activity is blowing up balloons and tying them together, taking a picture of each one. So linear, 2, you're going to get a line. 3, you're going to get a triangle. 4, you're going to get this tetrahedron, and then 5 and 6 you'll see when you do it. It's kind of cool. So that's all you need to do for the second activity. Any questions on that one? It really works well because some of these shapes are really weird. So it kind of helps visualize them when you actually like put them together. You'll see that, oh, right, that's why it's that shape. That makes a lot more sense now. So, and I think I also put a, did you get the announcement where I put a guide to all the molecule shapes in an announcement. So you don't have to memorize all these shapes because I can't remember trigonal, bipyramidal, and octahedral and all this kind of stuff. All you need to do is figure out who's the central atom. We use the Axe body spray rule. A is the central atom. X is the total number of bonds around it. And E is the total number of lone pairs of E electrons around it. And then you figure out using this formula what shape it's going to be. So I gave that in, I put it on the Canvas page, and I put it in an announcement. So hopefully you have that. Have people seen that announcement with the attachment in it? Hopefully, yes. If not, just go back to Canvas, it'll be there. So you don't have to memorize these shapes. What you do need to know is how many electron domains there are. That you need to be able to calculate. Okay. So molecular geometry. So here we're going to start using the bond making kit. Hopefully you still have this. Because we're going to be constructing three-dimensional models of these molecules from group 1. Because what it will do is it'll help you, because you need to basically draw the three-dimensional structure for each one of those molecules that you chose, 3 from group 1, 3 from group 2, 3 from group 3. So the way to do that is they give you sort of a rundown of which of these to use for each individual atom. So the ones with the white, a single white prong actually is hydrogen. So that's these. So these will be your hydrogens. They basically just have a single prong because they only form one bond. The green ones will be for other atoms that only form one bond. Typically like chlorine and fluorine and that sort of thing, because we give it like a chlorine green color. 3-prong dark brown will be for things like boron. So it only forms 3 bonds. So you can see you've got a little hole in the middle and 3 places to put bonds. Black with 4 bonds is carbon. And you can sort of see just from this what the shape is. Notice how this is a tetrahedral shape. It already helps you to show you what the tetrahedral shape of a 4-electron domain molecule will look like. Blue with 4 is nitrogen. 3 bonds, and one of these prongs is going to be a lone pair. Red with 4 is oxygen. So for oxygen, 2 of the prongs are going to be lone pairs and 2 of the prongs will be bonds. And then these white tubes put together, you just use these to put the molecules together. So I'll just give you an example of one and how you use it to help. So for instance, let's do CO2. So CO2, we put the molecule up here, CO2. And so this is what it's going to look like. So how many domains around central carbon?
2.
2, right. It's got a double bond on one side, it's got a double bond on the other. How many lone pairs does the central carbon have?
0.
None. Nada. So what's the geometry of this molecule going to be? Remember, it's got 2 electron domains. What shape is it?
Linear.
It's going to be linear, exactly. And so because it's linear, what is this bond angle going to be? This oxygen, carbon, oxygen bond angle. What angle is that when you have a
180.
straight line?
180.
180. Yep, 180 degrees. And so if you're going to make the model for this, I think it's a good idea just so we start with carbon, right? So we got our carbon and we connect it to oxygen on either side. But notice when I connect my carbon to the 2 oxygens, it's not linear, is it? I'd say that's bent, right? That's like the same shape as water. That's bent. So why is this bent? And we're supposed to have a linear molecule. What's up with that? Why is this bent and not linear? Am I finished? What does each one of these macaroni shaped tubes, what do they represent?
1 bond.
1 bond, right. So how many bonds do we have around the carbon here?
2.
Just 2. And how many should we have?
4.
Should have 4, exactly. So we're not done. So we need to put another bond in between them. So I'll just do that now. So I'll connect the carbon with another bond to each of the oxygens on the outside. And look what happens. Now, what shape is it? I mean, it's a little bent, but what shape is this? Basically, you can't see the electrons when you're looking at a molecule. You just see the atoms. So what shape would that look like if you just see the atoms?
Linear.
Yeah, it looks linear, right? Because they're all in a line. So it becomes linear when you put the second bond between the carbon and the oxygen. So when you do the line drawing, it's just basically it's the same as the Lewis structure because it's just a straight line. Now, if you're going to do something like methane, CH4, how many domains? So that looks like this, right? So we've got 1, 2, 3, 4 hydrogens around the carbon. How many domains in that one? Around the central carbon. How many areas of electron density are around the carbon?
4.
4, exactly. And how many lone pairs on the carbon? As usual.
None.
None. So go to your table that I gave you and look that up. So that would be A, XE, Axe body spray. So 4 domains, 4 bonds, 0 lone pairs. You look that up, and that geometry is going to be what? Anyone? Oops. Go back. That geometry is, and shape, because geometry and shape are different. Geometry is like the overall group that the molecule's in. The shape is the actual shape it has. The geometry is a tetrahedral. And in a tetrahedron, the bond angles are around 109.5 degrees. Now, when you do your line drawing, you have to show that the actual three-dimensional shape, because it's not a line, and it's not trigonal planar in a plane. It's not a two-dimensional shape. It's a three-dimensional shape. And so in order to do that, we need to sort of represent that it's got a three-dimensional shape. So to do that, you have you put your carbon in the middle. You have, oops, I could do that better. You show this sort of wedge coming out of the screen with your hydrogen there. You have another one with a hatched line that looks like it's behind the screen. And then the other 2 carbons are in a plane. So you draw it like that. It sort of roughly looks like it has a three-dimensional shape. Oh, what's wrong, Drew? Okay. Okay. So do that for the 9 molecules you've chosen. So now we're just going to look at, any question? Let me just go back. Sorry, I'm going fast because there's a lot to cover. Anyone have any questions about find that table? Definitely find the table because it will help you deal with geometries, shapes, and bond angles. You don't have to memorize the bond angles either. All that information's in there. Okay? All right. So bonding and polarity. So who can tell me the difference between an ionic bond and a covalent bond? Got ionic here. What's the difference between an ionic and covalent bond?
Ionic donates it, and then covalent shares the electrons.
Right. So in an ionic bond, one atom takes electrons from the other one. So what do we see in an ionic bond that we don't see in a covalent bond? Are there atoms? Everything's an atom in a covalent bond. What about an ionic bond? Is everything an atom? What are you going to find in an ionic compound? Hint, it's the first part of the word ionic.
The ions?
Yeah, they're going to be charged, right? In an ionic compound, you actually have charges. So sodium chloride, in sodium chloride, the sodium is charged, and so is the chloride ion. They both have a charge. In a covalent bond, neither one of the atoms is charged. They may not be sharing electrons equally, but generally you're not going to see a charge. Sometimes you do, but not too often. So what's the difference between a polar covalent bond and a non-polar covalent bond?
The nonpolar one shares the electrons equally, and the polar one, like one atom pulls more on the other.
That's right. Yeah. In a nonpolar covalent bond, basically they're sharing, like, everything's groovy. They're sharing their electrons relatively evenly. And in a polar covalent bond, one of those elements is pulling that electron density toward itself. And when that happens, you get something that looks like this. So here, I've got hydrogen chloride, or HCl, hydrochloric acid. And we know the chlorine has a much higher electronegativity than hydrogen. And so this pair of electrons in the bond is going to be spending more time closer to the chlorine than it is from the hydrogen. So what happens, why do we call it polar? Well, we call it polar because it creates a dipole. It creates a dipole where, and what is a dipole? Anyone tell me what a dipole is? What's a dipole? It's where we get the term polar.
Isn't it like equal and opposite charged poles?
Oh, yeah. I mean, that's one definition where you have a charge here. So like, again, so between the sodium and chloride, that would definitely be a dipole because we have basically a whole positive charge here and a whole negative charge here. But what about if we don't have a full charge? What if we have a partial charge? Can that be a dipole too? Like an HCl? So this is definitely a dipole because I have two poles, a positive pole and a negative pole. That is the definition of a dipole. But what if this hydrogen, we say, has a partial positive charge, and this chlorine has a partial negative charge, meaning that those pair of electrons, they haven't abandoned the hydrogen completely. They spend a little bit of time near the hydrogen, but not completely. So hydrogen has a partial positive charge, and the chlorine has a partial negative charge. So can that be a dipole too?
Yes.
Yes, that's also a dipole. It's not as strong a dipole as this one because there you have a full charge. You have something that has a full positive charge, something that has a full negative charge. One has lost an entire electron. The other one has gained an entire electron. Whereas here, one side of it has lost most of an electron because it's spending more time with the chlorine, but it hasn't lost it completely. So it has a partial positive and a partial negative charge. And so the size of this dipole is going to be dependent on what? It's going to be a difference in something. The bigger the difference, the bigger the dipole. Difference in what?
Electronegativity.
Bingo. Yeah, the difference in electronegativity. So basically, the bigger the difference in electronegativity, the bigger the dipole. So if I have a carbon-hydrogen bond, carbon has electronegativity around 2.5. Hydrogen has an electronegativity around 2.1. So that's not very polar at all. That's barely polar. That's about as non-polar as you can get without it being completely non-polar. So when we draw a dipole, if you remember, we draw it like this. We make a little arrow that looks like that. The arrow head points at the more electronegative element, and this, what looks like a positive sign, is pointing at the lesser electronegative element, showing you where the partial positive charge is going to be. So what direction would we put the dipole for that carbon-hydrogen bond? Who would be pointed towards, the hydrogen or the carbon? Remember, we point it at the element that has the higher electronegativity because it's the one that's going to be slightly more negatively charged. So who's that going to be, carbon or hydrogen?
Carbon.
Carbon, slightly higher, right? Carbon is slightly higher electronegativity. So when I draw my dipole, remember this is a bond dipole. We'll get into bond dipole and molecular dipole in a second. But the bond dipole is going to be really small and pointing at carbon. So itty bitty dipole there. And because the difference in electronegativity is really small, so that dipole is not going to be very strong. Now let's look at a hydrogen fluorine bond. So again, hydrogen has an electronegativity of around 2.1, and fluorine is the highest there is at 4.0. So is this going to be a polar covalent bond or a non-polar covalent bond? What's the difference in electronegativity? Four point oh and 2.1. What's the difference? Anyone still out there? What's the difference in electronegativity between hydrogen and fluorine here?
Oh, 1.9.
1.9. So that's super ionic. That's practically ionic. The only reason this doesn't form an ion is because fluorine is so electronegative, it doesn't let the hydrogen get away. So that's pretty much the only reason this is still a covalent bond. So now, which direction do we point the arrow? Do we point, remember the arrowhead points at the more electronegative atom. Do we point it at the hydrogen or do we point it at the fluorine?
The fluorine.
Point at the fluorine. Now, unlike this dipole, which was small, this one's going to be huge because it's a big difference. So we make the dipole, we make the arrow itself a lot longer to show you that it's bigger. So the size of the arrow is basically indicates how big the difference in electronegativity is. If it's a small difference, you make it small. If it's a big difference, you make it big. So it'll be pointing like that. So when we come to activity number 4, take the same molecules, and so it's basically asking for what are the difference in electronegativity between the central atom and the other atoms around it. So for instance, if I have ammonia, those would be NH bonds. And I believe nitrogen is 3 and hydrogen is 2.1. So the difference in electronegativity is 0.9. So what would be the bond polarity? So the bond polarity just means you write down the bond and you draw the arrow showing in which direction, whether it's polar. So is this a polar bond? A nitrogen-hydrogen bond?
Yes.
It is. Who's more electronegative?
Nitrogen.
Nitrogen. So it's going to look like that. So that's how I draw my dipole, pointing toward the nitrogen. So this question here, dipole moment. Dipole moment is just basically, that's how we measure the size of a dipole. We say it's a moment, and it's so sweet. You probably don't remember the unit for dipole moments, but they're measured in Debbies. It's so cute. They're measured in Debbies, little Debbie snack cakes. So the question here, why it says dipole moment, is does the molecule have a net dipole? So what's the difference between, let's go back to NH3. I'm going to draw it like, this is what it's going to look like. Oh, that's a hydrogen. That's a hydrogen. And that's a hydrogen. So each of those bonds is polar, but that does not necessarily mean that the molecule is polar. For instance, carbon dioxide, there's a dipole pointing in this direction because oxygen is more electronegative than carbon. And there's a dipole pointing in this direction because this oxygen is also more electronegative than carbon. But is CO2 a polar molecule or not?
No.
It isn't, right? I mean, one of the things, we don't expect a polar molecule to be a gas at room temperature. And carbon dioxide is a gas at room temperature. Water is helipolar, and it is a liquid at room temperature. And we'll learn about why that is a little bit later. The more polar things are, the more they stick together. So they tend to be liquids and solids. Non-polar molecules tend to be gases: hydrogen, nitrogen, oxygen, chlorine, fluorine, CO2. Non-polar things tend to be gases at room temperature. So how could CO2 be non-polar when it has two polar dipoles in it? It has two dipoles in it. How can it be non-polar? I mean, there's a difference in electronegativity between the carbons and the oxygens. There's two bond dipoles in there. But what's the orientation of them? What's the orientation of these two bond dipoles? This one and this one. What can you say about them? About their orientation? What are they relative to each other?
They're going in the exact opposite direction.
Exact opposite directions. So they're going in precisely opposite directions, and they're precisely the same size. You can see, because one carbon-oxygen bond is going to have the same polarity as the other carbon-oxygen bond. They have exactly the same, the dipoles are exactly the same size, and they're pointing in exactly opposite directions. And so they cancel each other out. And that is what we call a net dipole. Remember, net means after you add everything together, add and subtract everything together, what do you have at the end is the net. So the dipole moment is the net dipole moment. Does it have a net dipole? And so the dipole moment is, does it have a net dipole moment? Yes or no. If it does, it's polar. If it doesn't, if everything cancels out, then it doesn't. So CO2 has no net dipole moment because they're equal and opposite and cancel each other out. Now, let's look at ammonia here. Do those three bond dipoles cancel each other out? I'll accept an answer from anyone but Brandon. He's doing all the heavy lifting tonight. Is that thing going to have a, do those dipoles add, are they additive? Do they add up or do they subtract each other? What do you think? Are they pointing in the same direction or are they pointing in opposite directions? What do we think? Same relatively the same direction or in opposite directions?
Same direction.
Yeah, they're all pointing sort of up toward the nitrogen, right? Now this, if this was, okay, well, I'll show you in a second. So yeah, so they're all pointing up at the nitrogen. And because this is a tetrahedral shape, because we have 1, 2, 3, 4 bonding regions, that is a tetrahedral shape. And the base is these 3 nitrogens all sort of pointing at the middle. And so when we add them all together, what we get is a net dipole that looks like this, sort of pointing up and in the direction of the nitrogen. So does that have a net dipole moment? Yes. And the polarity? Polar. Now, let me show you what we had before. We had BF3. Remember we had BF3 at the beginning? 1, 2, 3. So what's going to be the shape of this molecule? It has 3 electron domains.
Trigonal planar.
There you go. Yeah, it's going to look like a triangle, right? With the boron in the middle. Now, what are the bond dipoles going to look like? I've got boron and fluorine. Who's more electronegative? Easy question, since no one's more electronegative than fluorine. So doesn't matter who fluorine's bound to, except itself, it's going to be more electronegative than everybody. So the bond dipole is going to point at the fluorine. So the direction of each bond is going to look like this. They're all going to look like that. So let's do that. Let's put them there. So I got 1, 2, 3. So I have 3 fairly substantial bond dipoles. Is this molecule going to be polar? Is there going to be a net dipole moment? So when you add these 3 together, are they going to cancel each other out or are they going to add up to something? What do you think? Sadie, I see your box is lit up here. Are you thinking about it? You're just itching to answer the question.
I don't know.
So remember, this with CO2, whoops, the CO2 was equal and opposite. And so they canceled each other out. Can you say the same thing about BF3 here? Are they equal and opposite?
Yeah.
What do you think?
Yes.
Yeah, they are. They're equal and opposite. They're all the same size because they're all boron fluorine bonds. They're all three, they're identical bonds, and they're exactly 120 degrees apart. So it's completely symmetrical, and they're all pointing in the same direction. They're all pointing away from the boron. So net dipole moment, no, making it nonpolar. So the same thing is true for CH4, for methane. With methane, you've got 4 regions of electron density around the carbon. So you have the tetrahedral shape with carbon in the middle, and 1, 2, 3, 4 hydrogens around it. And each one of those dipoles points toward the carbon. So we got 1, 2, 3, 4. But basically, these are all equal and opposite too. They're small dipoles because the difference isn't that great, but they're all pointing in the same direction, and they're all equal and opposite. So basically, they cancel each other out as well. And so no net dipole moment, and that is also nonpolar. All right. So data table 2 here, basically all this is, you can just nail this in a second. Basically all you need to do is just, you should have a table of electronegativities. If you don't, they're real easy to find on the web. Or if you go to ptable.com, I don't know if I've mentioned that before, I probably have, periodictable.com. It's just go there. It just basically has all the information you need. You can see it has all the elements, it has all the elements, but it has all the atomic masses. It has all the different charges that the transition metals take. It has the electronegativities. It's got, what their ionization energies are, all that stuff. So just check that out. So all you have to do is just give the electronegativity difference between a hydrogen and a hydrogen. Gee, I wonder what that difference is going to be. What's the electronegativity difference going to be between hydrogen and hydrogen?
0.
Yeah, it's going to be buckus. So what kind of bond is that? So you got basically you have 3 choices. It's going to be polar covalent, nonpolar covalent, or ionic. So with an electronegativity difference of 0, what type of bond is that going to be?
Nonpolar.
It's going to be super nonpolar. Nonpolar covalent. So nonpolar covalent. And so bond polarity, all you need to do is just draw HH without a dipole. That's what they're looking for there. So bond polarity is to HH with no dipole. For nitrogen and hydrogen, the electronegativity difference would be the difference between, I think, 3 and 2.1, so it's 0.9. So what kind of bond would that be? Polar, nonpolar covalent, or ionic? Remember, if the difference, if delta En, or difference in electronegativity, is greater than 0.3, we say it's a polar bond. If it's greater than 1.8, we say it's ionic. So where does 0.9 fit in? Nonpolar, polar, or ionic? Cassandra, help us out. Polar, nonpolar, or ionic?
You said if it's above 0.3, it's polar.
Yep.
Okay, then polar.
Yep. Polar covalent bond. So say polar covalent. And then when it's time to draw the polarity, I've got my N and my H. So where am I going to put the dipole? Pointing at the nitrogen or the hydrogen? Oh, come on, don't all answer at once. Which direction does it point? Does it point to does the arrow point to the more negative or the less negative? The more electronegative or the less electronegative?
The more electronegative.
So where am I, so how, when I put my dipole, who am I going to be pointing it at?
Nitrogen.
Yeah, right. So there you go. So it looks like that. So yeah, and this just, I think that table has about like 15 or 16 of these. So you should be able to blast through that pretty easily. The next part, I don't know if you've had any experience with. Has John been talking about hydrocarbons yet in class? It's a yes or no. Is this new stuff, hydrocarbons?
I think in this week's he was talking about it.
Okay.
I saw in the other class that the other lab class that they weren't doing activity 5.
Oh, they weren't.
Yeah.
Oh, let me see. Actually, you might be right. I need to check the report. You might absolutely be right, which would be awesome. So I need to find. So in your report, is that not there?
It's there, but I just saw in like the other class that it said they weren't supposed to do activity 5.
Let me see. But yeah, but if it's in the report, then we're going to be responsible for it. I don't want to. Damn, I can't find it. Oh man. All right. Let me double check. Let's go to the source here.
Oh, I'm looking at the lab report. I don't see for activity.
Activity 5.
5. Yeah, I don't see for activity 5.
Yeah, that would work for me because then we could, go to bed. I don't want to leave you guys in a lurch if it's going to be required.
Oh, sorry. Wait. Okay. Because I kind of just scrolled down. Never mind. It's just one. I think it's the data table 3 is supposed to be for activity 5.
Where is the? I'm on the website. I'm on the Canvas. I can't find the lab report. The sort of the structure of the lab report, the Word file with the. Where is it?
It should be on modules, and then this week's or last week's.
That's what I thought, but I couldn't find it. So it's in week 9. Oh, there it is. Okay. Okay. Let me just, yeah, sorry. I really thought I had this. So, right, data table 3. Here we go. Here we go. Yes, so actually there is quite a bit here. So okay. So let's just sort of briefly get through this as quickly as we can. So let's go back to. So we will have to do some of this, unfortunately, but I'm going to be grading it, so I won't be mean. But just briefly, so hydrocarbons, not terribly surprisingly, just have, for the most part, hydrogen and carbon in them. So there's like three basic ones we're going to be dealing with. Where's my annotation? So the first kind are just basically called alkanes. Alkanes have all single bonds between all the carbons, and so they can move around. They can freely rotate and take all kinds of different shapes. If they're all in a line like this, you can see that each carbon is one right after the other. We call that the N form. And the name we get comes from, we get this Latin root here, followed by ane. So it's pentane, hexane, heptane, octane, nonane, decane. So pentane has five. Now, there's a lot of different ways we can put pentane together. One is we can have what's called a methyl group, CH3, with this carbon connected to somebody else, is called a methyl group, not methane, because it doesn't have all four of its carbon is bonded to another carbon. So it's a methyl group. Now this can move around. It can be bonded to the second or the third. Now notice when we, so we call this 2-methyl butane. Butane has 4 carbons in a row. 1, 2, 3, 4. And a methyl group coming off the second one. So we call that 2-methyl butane. But notice that it has exactly the same number of carbons and hydrogens as this one. They're exactly the same formula. They're just put together in different ways. Now we call these isomers. Isomer molecules have exactly the same formula, but different shapes. And that's an example here. And so this is 3 different ways we could make the same C5H12 molecule. Each one of those has 5 carbons and 12 hydrogens, but they're all different. They have different shapes. This one would have like a ball shape, basically. Oh, and there's also an error in there. Does anyone see what the error is in that molecule? It's getting late, so what's the error there? It's the carbon in the middle. What's wrong with it?
It's missing some H's.
No, actually, it's got 1 too many. How many bonds is that carbon making?
4.
No, it's making 5 because it has a hydrogen. So it's actually making 5 bonds, and carbon can't do that. So actually, there shouldn't be a hydrogen there at all. So that carbon in the middle should have no hydrogens attached to it because it's making 4 bonds. It doesn't have room for anything else. So that's actually a typo. So alkanes, all single bonds. So there's lots of different ways to show these. This is just the straight up molecular. Oh, let me go back. It's just the straight up molecular formula. This just tells me how many of each atom there is. That's it. It doesn't tell me what shape it is or what form it's in. The next one is called the structural formula. That shows you so how all the atoms are connected to each other. The condensed formula is basically simpler than this. It gives you, it doesn't have all of the hydrogens there because we know they're there. So it just shows you that this carbon has 3 hydrogens, this one is 2, this one is 2, this one is 2, this one is 3. So it's simpler, but we get the same idea. Now, the really simple way of showing it is what's called a skeletal model. In a skeletal model, we just show the carbons. That's it. We don't even include the hydrogens. So this just says that there is 1, 2, 3, 4, 5 carbons, and that they're all attached in a line. And we just assume that the rest of the hydrogens are there. So this carbon on the end, carbon 1 and carbon 5, are only attached to another 1 carbon. So there's room for 3 hydrogens. Carbon 2, 3, and 4 are connected to 2 carbons, so they only have room for 2 hydrogens. So it's going to be CH3 on the ends and CH2 in the middle. Now this one is called, shockingly, the ball and stick model. And that's basically what we're making here. This is like a ball and stick model. That shows the number of atoms, and it has the advantage of showing you the shape. So you can see by building this thing, we get to see what the shape of it is. And then last, space filling model shows you the 3-dimensional shape. So it doesn't show you the bonds because we don't really see the bonds in a molecule. We just see the atoms. We don't see the electrons. They're way too small. We just see how the atoms are arranged. And that's what the space filling model is. It gives you the overall shape of the molecule without seeing the bonds. And so the carbons are going to be bigger than the hydrogens. Just like, so the white ones are hydrogen, the black ones are carbon. Oh, let me clear this out. So alkanes, we call those saturated hydrocarbons because every carbon atom is a single bond. You probably heard of, who's heard of saturated fat, right? Saturated fat, bad. You know why they're called saturated fat? What's the difference between a saturated fat and an unsaturated fat? Anyone know the difference?
There's more hydrogen on the saturated fats than there are the non-saturated.
That's right. And the reason is because alkanes are saturated hydrocarbons, and fats are basically long hydrocarbons with a group on the end, like an acidic group or a basic group on the end. But it has these long hydrocarbon chains. And saturated fats will look like this. They're all single bonds. Now, the alkenes, we could say they're unsaturated because they have at least 1 double bond. So alkenes have double bonds in them. And so an unsaturated fat has at least 1, or unsaturated fat has 1 carbon-carbon double bond, and a polyunsaturated fat has multiple carbon double bonds. And they have different shapes to them. So alkanes have this general formula. If you have n number of carbons, you have H2n plus 2 hydrogens. So if I have 4 carbons, I have 2 times 4, 8 plus 2, 10 hydrogens. It doesn't always because they're all single bonds. Now, the minute you have a double bond between the carbons, basically you lose 2 hydrogens, because where there used to be room for 2 hydrogens, they're now gone. So now our formula is going to be twice as many hydrogens as carbons. So now if I have C10, I know I'm going to have H20. And these are the different shapes they can take. So we call this cis butene and trans butene because of these methyl groups. When you build a double bond, when you make the double bond, you'll see that it's static. You can't bend them. These things are locked in place. And so when you have a double bond like that, if these are two carbons, they're locked. They can't rotate. So if anything else is attached to them, they stay in that place. So these two methyl groups here, this one and this one, are basically locked on the same side of that double bond. So they're going to be next to each other. They're going to be on the same side. And if they're on the same side, we call that cis for same. If they're on opposite sides, like they are here, here's the one methyl group is on the top, the other methyl group is on the bottom. They're locked on opposite sides. Opposite sides, we just call that trans. So those are isomers also, because they have the same formula, but on opposite sides of the bond. All right. Keep going. So alkanes, all saturated bonds, all single bonds. Alkanes, one or more doubles. Here we go. Alkynes have triple bonds. So alkanes, singles. Alkenes, E-N-E, oops, damn it. So A-N-E, single bonds. E-N-E, double bonds. Y-N-E, triple bonds. So here we have the triple bond. What shape do you think this molecule is going to have? How many electron domains around each of those carbons?
Two.
Two. And so if there's two electron domains, what shape does it make?
Oh, linear shape.
It's linear, exactly. So these are going to be linear molecules. So they have very rigid bonds. You can imagine triple bonds are really locked in place. So nobody's going anywhere, and it's linear. So basically it just rotates. It doesn't even spin. So you can have circular alkanes. You can have circular. So for instance, I can have cyclohexane. And all cyclohexane would be is that I would have 1, 2, 3, 4, 5, 6 carbons in a row, but they're joined. The first carbon and the last carbon will be joined together. And each of them would have 1, 2 hydrogens on either side. Now there's a special form of ringed hydrocarbons called aromatic hydrocarbons. Why do you think they got that name? Why do you think they're called aromatic hydrocarbons? Take a wild guess.
Because they smell good?
They smell really strong. They smell really strong. And what this aromatic hydrocarbon is they have a ring structure, generally with 6, and they have alternating double and single bonds. So this is the most famous example, benzene, and it has, you can see a double, and then a single, and then a double, and then a single, and then a double, and then a single. So each carbon has a single bond on one side of it and a double bond on the other. So they only have room for one hydrogen each. So C6H6. Now, the interesting thing about benzene, there's a lot of interesting things about benzene, is it's flat. It's a planar molecule because of those double bonds. But there's a number of different ways you can draw it. And so one of the things that we can do is, so if this is carbon, if we have carbon 1, 2, 3, 4, 5, and 6, you see here we have the double bond between carbon 1 and 2, 3 and 4, between 1 and 2, 3 and 4, 5 and 6. But it could easily be, we could just move them over. We could easily just flip this. So this is a double bond. This is a double bond. And this is a double bond. So then that would make it look like this. 1, 2, 3. So you see how we just move the double bond one position, right? You have to see how we do that. So we have the double bond used to be here, then we moved it to here, and then we moved it to here. So basically what that means is that these double bonds basically move around and around and around and around and around. That's one of the reasons why it has these special chemical properties, and it's aromatic. Because benzene doesn't really have single and double bonds. It actually has an average of 1.5 bonds between each carbon. If it really did have double and single bonds, we would expect that the distance between these carbons would be different, right? Which is longer, a double bond or a single bond? Anyone know? Carbon-carbon single bond, carbon-carbon double bond. Which one is longer? Which is the greater distance between the two carbons? Single or double? What do we think? You can look it up too. Double bond is shorter. The reason is you need to move those two atoms closer together to get the second pair of electrons to be shared. They need to be pushed together a little bit. So single bond is actually longer than a double bond. A triple bond is even shorter. So if that were the case, we would expect 2 different bond lengths for carbon-carbon bonds in benzene, but we don't see that. They're all exactly the same size. They're slightly shorter than a single bond, but they're longer than a double bond. They're sort of in between. And we'll get into bond order a little bit later. But that's why we have all these different ways of representing them. We usually just draw it like this, with 6 sides and just a circle in the middle to show you that they're all basically all the same. And we don't even bother putting the hydrogens on it. So for these exercises, basically they just want to show like what kind of bonding is in alkanes, alkenes, and alkynes. Basically single, double, triple. What's the general formula? That's right there in the instructions. And then here's some examples of different types. We have an alkane at the top, an alkene in the middle, and an alkyne at the bottom. And so what's the three-dimensional structure going to look like? What's the shape going to be? Can the bonds freely rotate? And you can show that, like I said, by making the model. Double bond doesn't rotate. If we turn these into single bonds, you can see we can freely spin this around, whereas you can't do that with a double, and you certainly can't do that in a triple. So, and bond strength. What's stronger, double, single, or triple bonds? It's fairly obvious. So for this table, they just want you to draw different isomers of propane. Oh, sorry, not propane, butane. C4H10. So because it's C4H10, that says that it's N and 2N plus 2. That has to be a saturated hydrocarbon, so no double bonds. So just basically draw as many structural isomers as you possibly can. So just different ways of putting the carbons and the hydrogens together to make different shapes. And then these are isomers of butene, because now we have a double bond presented. So if you remember what the condensed formula was, that's back in the instructions, and the skeletal model is basically what shapes are these going to look like. Remember, this skeletal model looked like this. Well, for molecule 1, it's going to look like this. 1, 2. So it's got 1, 2, 3, 4 carbons, right? And there's a double bond between carbon 2 and 3. So all we need to do is that. That gives you all the information you need. So the double bond, you just make another line. So the skeletal model is pretty straightforward. For this one, you see it's going to be exactly the same. Molecule 1 and molecule 2 are going to have exactly the same skeletal model, whereas molecule 3, 1, 2, 3, 4. Where do we put the double bond for molecule 3? Here we put it there. Here we put it there. Where do we put it on the third one? Where's the double bond going to go?
On the first one?
On the very first one. So just go there. So that's the difference. So you can see organic chemists, like, you know, if they're in a hurry, these save a lot of time. So if you're making, especially if you're drawing like really long molecules, like a saturated fat, for instance, it would take way too long to draw all the hydrogens and everything else. So we use the skeletal model to help shorten this out. So for alkynes, draw the structural models of all the different forms of C4H6. Remember, you got to have at least one triple bond in there. And then determine which structures are the same. Like, for instance, if you put, for example, if you have, damn it. If you draw this, then compare it to this, that's the same molecule. You've just flipped it. So this would be 1 butine, and so would this. Because when we're naming where the double or the triple bond is, we always try and give it the lowest number possible. So that would be carbon 1, carbon 2, carbon 3, carbon 4. And if we're going the opposite direction, we try and give it the smallest number possible again. So now this is carbon 1, carbon 2, carbon 3, carbon 4. All right. And then we're going to finish up with the benzene and the different, so just ask for the skeletal models of benzene. So that basically is this, right? And the other one looks like 1, 2, 3. So are these the same? Are these isomers? Are those two structures isomers, or are they the same molecule?
The same molecule?
Yeah, they're identical, because all you have to do is just rotate it by, what is it, 1/6, there's 160 degrees. Just rotate it 60 degrees, it's the same molecule. So they're not isomers. And so, and I think on the instructions, they show you different places you can put chlorine. So dichlorobenzene means it's just benzene with, shockingly 2 chlorines on it. So there's 3 different places to put them. We can put them here, chlorine here, and a chlorine there. Or we can put a chlorine here and a chlorine there. And then the final one, we can put a chlorine here and a chlorine there. And we call them different forms. One is meta, one is para, and the other one is ortho, depending on where the chlorines are. When they're close together, it's meta, so meta. And when they're separated by 1 carbon, we call it para. And when they're separated by 2 carbons, they're opposite to each other, we call them ortho. So it'd be meta-dichlorobenzene, para-dichlorobenzene, ortho-dichlorobenzene. So are these molecules isomers, or are they the same molecule? What do you think? Is having chlorine, the 2 chlorines next to each other, exactly the same as having the 2 chlorines opposite each other? Is that the same molecule? We know they have the same formula. They're all going to be C6H4Cl2. So they're all going to have the same formula. But are they exactly the same molecule? Or are they different? What do you think? Be last question of the night, then we could go home. Oh wait, we are home. Basically, with an isomer means they have different shapes, right? And isomers are not exactly the same. They have different shapes. So to those 2 molecules, one with the 2 chlorines next to each other, and the one with the 2 chlorines on opposite sides of each other, do those molecules have different shapes?
Yes.
Yes. And so are they isomers, or are they the same molecule?
Isomers.
Right, exactly. They're not the same molecule. And actually, you could separate them. They would have different boiling points and melting points. They're different. They're structurally different. They're chemically different. They have the same formula, but they're chemically different. These 2 forms of benzene are identical in every way. They're exactly the same thing. But having the 2 chlorines next to each other and having them far apart from each other gives you different chemical properties. So they're isomers, they're not the same molecule. All right, I think we're ready for bed. What do you think? Any other questions before we go? Got to be at least one question. We breezed through a lot of this stuff pretty fast, so. I will change the date for the report to Monday, so you can nap all week. Any questions? Thank you too, Rachel. Thanks for hanging out. All right, so if there aren't any more questions, we'll call it a night. I'm gonna go have some tea,